All right, so now we're going to move on past particles, and we're going to start dealing with collections of particles and or objects, as we call them, or things. Things that fit, real physical things that take up space in our universe here. And we're going to deal with the motion of these things, and it complicates things just a little bit for us. All right. The specific type of motion that we're going to be dealing with is that of rigid bodies. So first thing, we have to define what is a rigid body. And it's pretty obvious, but I'm going to say it in such a way that makes it kind of mathematically important or precise. Maybe not to the satisfaction of some mathematicians, but yeah, it'll serve our purposes. So a rigid body is one, so any body can be thought of as a collection of particles, associated with one another. And it's rigid if the distance between any 2 points within the body is constant. So here's a body that is clearly not rigid in the, easily understood sense. And I've sort of drawn 4 points here. And you can see as I flex it, the relative distances, say, like, as I flex it in this direction, this distance here gets longer, this distance here may get longer, this distance will get a little shorter, this distance will get a little shorter, and this distance will maybe remain constant. You know what I mean? Roughly. Doesn't change much. However, a rigid body is one where all of those distances would remain constant over time. And so it's the type of motion that we're going to be considering is that limits us to 2 cases: simple translation, where the body is just moving from place to place, and then a rotation about some fixed axis, or maybe it doesn't, rotation about some axis, and reference point. So so what we can do is we can describe the general motion as a translation of some reference point, and then a rotation about that reference point within the body. Okay, so and we've dealt with translation up until this point. Because we are dealing with particles, the only type of motion a particle can undergo really is that of translation. It doesn't make much sense to rotate something that does not have any physical extent, right? So when we're talking about collections of particles, now we have a situation where rotations mean something. That means that this point is going to move relative to this point. When we're doing translation, you can think of it as if the relative distance, or the vector describing the relative position of this point relative to this point, is constant, right? But now when it's rotation, the direction is changing. But because it's rigid body motion, the magnitude of that relative position is not changing, just the direction, which is going to imply some important mathematical object or aspects that we can use to solve problems. All right. So there's an important point about rotations that we need to first establish, and that involves this idea of how do we combine different rotations and things like that. So let's first talk about finite rotation. Now, how do we even describe rotation? Well, so rotations can be described by giving an axis and an angle. Or, in other words, a direction and magnitude. So in that way, it's very similar to a vector. Okay? So an axis is a direction, and an angle would be a magnitude. However, if we're talking about finite rotations, they disobey one important aspect of vector mathematics, and that is that finite rotations are not commutative. That is to say, if I try to add together two rotations in this order, it is not the same as adding them in the opposite order. Okay. Now, I want to give you an example here to make this concrete. But so if I take theta 1 is a 90-degree rotation about the x-axis, and theta 2, these are two different rotations, is a 90-degree rotation about the y-axis, then here's x and y, and then so z would be pointing out directly. Then if I have two objects oriented the same way, so these are two objects oriented the exact same way, right? So when I place them down here. Now, on the first one, I'm going to do theta 1 plus theta 2, which means I'm going to rotate about the x-axis using the right-hand rule. 90 degrees would be a rotation this way, 90-degree rotation. So that's about x. Now I'm going to rotate about y, which would be in this direction. You wind up in that orientation. Now, if I were to do it in the opposite direction, now I'm going to rotate 90 degrees about y, then 90 degrees about x. So let's see here. They clearly don't wind up in the same orientation. So we can't add finite rotations in that way. All right. So for that reason, finite rotations with a definite value, definite angle of rotation, are not vectors. So they can't be treated that way. Okay. However, infinitesimal, so if I can build up finite rotations by adding together several tiny rotations. All right. I do those, if they are in fact infinitesimal, I can do those in any particular order. So in Cartesian coordinates, this would look something like this. Now, why is that? So I can add them in this x, y, z direction, or I could reverse. So this would be a rotation about the x-axis, about the y-axis, and about the z-axis. That's because each one of these is essentially a zero rotation. When I'm talking about infinitesimal, I'm talking about the limit as these values approach zero. So this, in fact, d theta, as described just in this way, is essentially a rotation of 0 degrees, or the limit. It's a limiting factor, if you guys remember, in calculus. So this is a kind of a useless thing. However, say the ratio of a small rotation with a differential time, now that could be useful. This is you can start to see this is going to be a velocity of sorts. So it's going to be like a rotational velocity. And so this is meaningful. This is a vector, and we call this omega, the Greek letter omega. And that is, in fact, a vector. Okay, and then we can take the time derivative of it, and we call that alpha, or the angular acceleration. So this is called the angular velocity, and alpha is just the time derivative of the angular velocity. It's called the angular acceleration. And I have, I got a little demonstration I'm going to show you here in a second. Okay, so what we have here is a little illustration of the 3D rotation of this cube here. And this is under the blue arrow represents the angular velocity, and there's a red arrow which isn't quite visible right now, but that'll represent the angular acceleration. So as you can tell, if I increase the magnitude of the angular velocity, the rotation rate increases, which is as what could be expected. A couple things to point out here. I chose to represent this rotation about the center of the cube, and so that was a choice, and that choice will be highly dependent, or the choice you make is highly dependent on the details of the problem you're trying to solve. And then also notice that the velocity, or the motion of all these points, are basically, they form circles around that axis of rotation, which is that'll come in handy when we start to define relative motion between points. Okay, now, like I was saying, the choice of reference point is somewhat arbitrary, but dependent on the problem. And so if I decided, rather than using the center of the cube, if I decided to use one of the corners, say, you'd get rotation like that. Now, this is under constant angular velocity. And what if we tried to to really see the relationship between the angular acceleration and angular velocity? It would be more appropriate to do something a little bit more complicated. So notice, so what we have here is everywhere the blue arrow, the cube is rotating in a way described by the blue arrow. The relationship between the points and the blue arrow is not fixed. Okay, it just describes at all times how the cube is rotating. Then the red arrow represents the angular acceleration, and it describes how the angular velocity is changing with time. All right, so an even more sort of complicated situation would be something like this. And notice that the angular acceleration is at all times tangent to a curve traced out by the head of the angular velocity, which is what you would expect, right? This is the angular acceleration is going to wind up being the derivative, the time derivative of the angular velocity. So moving the reference point back to the center of the cube, if we weren't, it would be difficult to discern exactly what the angular velocity and angular acceleration are doing just by observing the rotations of the cube. But we'll be able to distill this into vector algebra and calculus and stuff, and be able to make sense of it in when we start solving problems. Now the last aspect to consider is general motion. Is a situation where not only is the cube undergoing rotation, but it may also be undergoing translation. So in this situation, I have the cube is translating along, it's still rotating the exact same way, but now it's translating along the x-axis. So it may even be, if you were simply just looking at the cube, it may be even more difficult to discern these sorts of things. But it's a simple vector addition. This complicated motion just gets vectorally added to that translation. In fact, the motion of every point is associated with that rotation, but then just a simple vector addition with vector addition, I guess. So let me see. So this black vector represents the translation, and and it has in this case it's moving at constant speed, so the linear acceleration is going to be 0, but it has a linear velocity, and if we're superimposing that on here as well, you would see it simply pointing in the same direction as the path traced out by the head of this arrow. All right, so to sort of put this, to finalize our discussion on the general motion of a rigid body, we're going to bring that translation into account and then describe how all of the points located within the body move relative to the reference point that you chose to describe the rotation. So say we have a body, some arbitrary shaped body, and here's our reference point, point A, and we want to know what point B is doing. And I think we discussed this. In fact, when we were dealing with this when we were talking about particles, because that's precisely what we're doing here. We're just discussing how these particles are moving relative to one another. So here's the position vector of our reference point, point A. Here is the position vector of B relative to A. So it's like as if we have another set of coordinate systems superimposed on top of A, and we're describing the motion of B in that coordinate system. And that's a fairly simple thing to do because as far as we're concerned, A is simply translating, not translating and rotating or anything strange like that. So this should be we went over this previously, so it's a pretty simple vector addition. So if we had a vector connecting the origin to B, it would just be the sum of the vector to A plus this the relative vector from A to B. All right, and then we can take the derivative of that. If we want to know the velocity of point B, that's just the velocity of point A plus the velocity of B relative to A. Now, because it's a rigid body, the A and B, this relative velocity has a very precise, or I guess like a special definition. So the velocity of B relative to A is just that angular velocity crossed with the position of the relative position of B to A. So therefore, the velocity of B is just the velocity of A now, I haven't really proven this to you, I guess, but this was in the video where we had the representation of the cube. This is just a way of writing. This is just the fact that the velocity of point B is perpendicular to both the position of point B relative to A. It's perpendicular to that, as well as it's perpendicular to the angular velocity. Okay, so this is kind of hand wavy, but this is the definition. This is a definition. So if I wanted the relative velocity of point B relative to A, it's just going to be the angular velocity times that, or crossed with the position of B relative to A, and then we can just differentiate that one more time. We take the derivative of the first, cross with the second, and we have to add the first cross with the derivative of the second. All right, and so this is just the angular acceleration, and VBA is given by this cross product here. So we get like this double cross product. Oops. All right. Now, because this is the definition, look, VBA, this is the definition of the velocity of B relative to A. And remember, if we take the cross product of two vectors, the result is perpendicular to both vectors. Right? So we can conclude from that, and this is a neat trick, if you know vectors are perpendicular, sometimes you can kind of take shortcuts. If so therefore, if I know that the velocity of B relative to A is perpendicular to both, but specifically it's perpendicular to the relative position, then if I take the dot product of those two things, it's going to equal 0, right? And then if I take the time derivative of this, it'll also equal 0 because 0 is a constant, right? So the dot product will equal 0, and then so I can take the derivative of the first, or I can just to spell that out a little better. And so the derivative of this is just the velocity, the relative velocity, derivative of the first times the second dotted with itself, plus the first times the, or dotted with the derivative of the second. And again, this will equal 0. So what does that mean? Well, we could even write this a little bit. We could translate this a little bit so that I don't know. This is just another way of writing that. Okay, so maybe that'll come in handy when we're solving problems. It's kind of a shortcut if the problem is set up in a very specific way, we could use something like this.